Today we will look at running a simple noise simulation in LTspice. In particular, I will go over how to set up a noise simulation to view both input and output referred voltage noise using a pre-existing op-amp model. I'll also mention a couple of tricks to learn more about noise contributors. Welcome to LTspice 4 Noise Simulations. I'm your host, Tyler Hutchison. First, we need an LTspice schematic that contains the circuit we'd like to analyze. In this case, we will use the LT6200, a unity gain stable, ultra-low noise, rail-to-rail input and output operational amplifier. The circuit is configured for a non-inverting gain of 10. As we can see by this AC simulation, the gain is 20 dB and the minus 3 dB point is at about 16.5 megahertz. Now let's set up a noise simulation. The easiest ways to set up a simulation is to either click on Simulate, Edit Simulation command, or right-click on an existing simulation command and finally select the Noise tab. The simulation parameters are a lot like an AC analysis. First, we specify the type of sweep, decade, then the number of points per decade, 100, then the start frequency, 100 Hertz, so we can see the flicker noise, and then finally the stop frequency, so we can see the circuits roll off. The two parameters that are different from an AC analysis are the input and output boxes. The name of the input source itself is typed into the input box, as the non-inverting input source is labeled VIN source. We type that into the input box. This is contrary to the output box, which requires a voltage node. Typically, this will be the output voltage node, labeled here as Vout. In this case, we will look at the noise voltage at the Vout node, the proper syntax for which is V, open parentheses, the name of the voltage node, Vout, then close parentheses. Then hit OK. To run the simulation, click either Simulate Run or right-click Run. We can look at the results by moving the mouse cursor over the output node and clicking. At low frequencies, we can see the flicker noise of the part. At higher frequencies, we can see this noise roll off. There are also a few other details to notice in the simulation. For instance, if you move the mouse over other nodes of the circuit, it merely shows the DC operating point. Since these nodes were not specified as the output, the noise referred to these nodes has not been calculated and they cannot be plotted. Also, by moving the mouse over resistors in the circuit, a voltage probe appears. If we click on a resistor, LTspice plots the output noise contribution of that resistor. We can see that the feedback resistor, RF, while a higher resistive value contributes less noise than RG, since the noise of RG is amplified by the circuit. If the user is interested in examining the output referred noise of only the op-amp, we can add the noiseless flag to the resistors. Right-click a resistor, and after the value, simply type the flag noiseless. Rerun the simulation, and the contribution from the resistors is now gone. Finally, let's make the resistors noisy again. And take a look at some additional information saved and calculated in this simulation. If we move the mouse pointer to the waveform viewer, right-click and select Add Trace, a list of available traces appears. Some of these are familiar. For instance, VO noise is the output noise, and VRF and VRG are the resistor contributions. However, the waveform viewer shows a few more variables. Gain contains the AC gain of the circuit, as if we had performed an AC noise analysis, though without phase information. VI noise contains the input referred noise, which is equivalent to the output noise divided by the gain. For more information about dot noise simulations and other LTspice tips and tricks, please visit us at www.linear.com/LTspice. Happy simulations!